If you're about to drop a few $100s on a 3D printer for your kid, here's something that might surprise you. The safer-looking, enclosed model could actually slow down their learning. I'm Kazuki Tanaka, and I've logged over 800 hours watching kids ages 8 through 17 work with both enclosed and open-frame printers in youth makerspaces. What I've found challenges a lot of the conventional wisdom out there.
You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the data, the script, all of that is 100% human verified and written by a real author. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that. If you've been listening for a while, thank you. It's really great to have you back. And if you're new here, welcome. I think you'll get a lot out of this one. We drop new episodes every Monday, Wednesday, and Friday, so you'll have a steady stream of content if you stick around. Today, we're talking about something I get asked about constantly: enclosed versus open-frame 3D printers for kids. Let's jump in.
So here's my verdict up front. Enclosed printers win when it comes to safer operation with materials like ABS and PETG. But open-frame models teach better troubleshooting skills and cost a whole lot less. Your decision really comes down to how much supervision you can provide and what materials you're planning to use. I've spent years running both designs with young learners, and the choice matters more than most parents realize. I'm going to walk you through how these two printer types compare across safety systems, thermal performance, maintenance access, learning outcomes, and real-world durability. By the end, you'll know which design actually fits your supervision capacity, your material plans, and whether you're building toward professional-grade additive manufacturing skills. Let me start with a quick comparison to frame this up. When we look at safety, enclosed frames give you HEPA filtration, finger guards, and automatic shutdown when the door opens. Open frames have exposed hot zones that require supervision, but they offer better visibility for teaching hazard awareness. On materials, enclosed printers handle ABS, PETG, and nylon because they maintain stable temps and there are no subscription fees to worry about. Open frame printers are really PLA-focused unless you add your own enclosure, but the consumable costs are identical either way. For troubleshooting, enclosed designs limit your visibility during a print, making it harder to diagnose failures as they happen. Open frames give you full visual and physical access, which teaches real-world maintenance habits. Thermal stability is a big win for enclosed printers, with only 5 to 8 degrees Celsius variance in the chamber, and 35% fewer warp failures in my testing. Open frames show 12 to 15 degree swings, and garage or basement environments cause adhesion problems. Price-wise, youth-appropriate enclosed models run $350 to $900, while open frame printers with equivalent build volume cost $200 to $500. And if you're thinking about a progressive skill path, enclosed printers mirror industrial systems like Stratasys and Ultimaker, preparing kids for prototyping careers. Open frames teach a mechanics-first approach and make it easier to transition to core XY builds down the line. Now, let's talk about safety systems and what kind of supervision you'll actually need. I've watched hundreds of kids learn on both designs, and the difference isn't just about preventing burns. It's about what I call the supervision tax you'll pay as a parent.
Take something like the FlashForge Adventurer 5M Pro as an example of enclosed safety design. Check the link below to see the current price. It's got magnetic door locks that prevent mid-print access. The 230-volt heated bed and 260-degree nozzle sit behind polycarbonate panels. The HEPA filtration is H13 rated, pulling VOCs before they reach your child's breathing zone. When my 11-year-old nephew ran 40 prints on this machine, I could actually leave the room during operation. That's something I would never do with an open frame printer. But here's the honest friction with enclosed printers. They create a false sense of invincibility. Kids don't see the nozzle dragging through a failed print. They don't witness the heated bed glowing. What I've found is that learners on open frame printers develop better hazard awareness because the consequences are visible. They learn what I call the touch test: hovering their hand 5 centimeters above the bed to feel radiant heat. They understand why you never reach into a moving printhead's path. Open frame models like the Creality Ender 3 V3 SE, check the link below for pricing, require constant line of sight for users under 13. The exposed gantry moves at 250 millimeters per second in some modes. Fingers can reach the nozzle mid-print. But this visibility teaches cause and effect faster than any manual ever could. After 6 months in my workshop with teen learners, the open frame group could diagnose bed adhesion failures 40% faster than the enclosed printer group. Power requirements matter for safety too. Most enclosed models need dedicated 15-amp circuits and shouldn't share outlets with space heaters or laser cutters. Open frame printers typically draw 180 to 250 watts, safe on standard outlets, but still requiring surge protection. You'll want to check your home setup for proper electrical infrastructure. Material safety is really the divider here. PLA, the beginner filament, emits minimal VOCs on either design. But if your kid wants to print ABS for impact-resistant robotics parts, or PETG for weather-resistant renewable energy projects, an enclosed printer with filtration is non-negotiable. I actually measured VOC levels in my 12 by 14-foot workshop. Open frame ABS printing spiked formaldehyde to 0.08 parts per million. OSHA's action level is 0.5, but why risk it? The same print in a FlashForge enclosure with the door closed registered 0.01 parts per million at nose height. Moving on to thermal performance and material versatility. Temperature stability determines print success rates more than any other factor. I've tracked this across over 200 prints per machine type.
Enclosed printers maintain chamber temperatures within 5 to 8 degrees Celsius of set point in my climate-controlled workshop. The Bamboo Lab A1 Mini, check the link for current pricing, holds 45 degrees Celsius ambient during ABS prints, creating a quasi-industrial environment. This matters for dimensional accuracy. Parts come off the bed within 0.1 millimeters of CAD specs consistently. I printed 20 identical 50mm calibration cubes on this machine. 19 of them measured 49.9 to 50.1 millimeters. One failed due to a clogged nozzle, which was my fault for using hygroscopic filament that absorbed moisture. Open frame printers fight ambient conditions constantly. The Ender 3 V3 SE in the same workshop showed 12 to 15 degree variance between bed level and 10 centimeters height. Now, this doesn't matter for PLA. I've run over 500 hours of PLA on open frames with 94% first layer success rates. But PETG? Forget it in winter. I logged 11 warped prints out of 15 attempts when my garage dropped below 15 degrees Celsius. You'd need to build a DIY enclosure. Cardboard and tape works, and I've done it, or accept PLA-only operation. Here's the cost reality. If you're serious about printing functional parts like robotics chassis, gears, snap-fit enclosures, you need ABS or PETG. An enclosed printer costs $200 to $300 more up front, but saves you from retrofitting an enclosure later. That Ender 3 plus a proper acrylic enclosure kit runs $475 total. You're in FlashForge territory anyway at that point. Filament subscriptions are a myth for both designs. You buy 1 kilogram spools, $18 to $35 depending on material, as needed. No vendor locks you into proprietary filament in 2026's youth market printers. But enclosed models unlock the full material palette: nylon for living hinges, TPU for flexible grips, even wood-fill PLA for aesthetic projects. If your learning path includes transitioning to professional CAD tools, material versatility becomes a capability multiplier. The one weakness with enclosed printers? Heat creep. When chamber temps hit 50 degrees Celsius during long ABS prints, the filament in the feed tube softens prematurely. I've had 3 jam-related failures on prints over 8 hours across enclosed machines. Open frame printers vent this heat naturally, making 20-hour PLA prints rock-solid reliable. I've done 3 18-hour landscape prints on the Ender without any intervention. Let's get into maintenance access and troubleshooting learning. This is where open frame printers become teaching tools instead of just appliances. Every print failure is a visible lesson on an open frame. Nozzle dragging through supports? Kids sees it in real time. First layer not sticking? They can watch the extruded line peel up. I've taught over 60 students on both platforms, and the open frame learners developed mechanical intuition 30% faster. I measured this by time to diagnosis on standardized failure scenarios. The Ender 3 V3 SE's CR Touch auto-leveling probe is fully exposed. When it inevitably needs recalibration, every 50 hours in my experience, students remove 4 screws, adjust Z-offset, and learn about mesh compensation. Compare that to the FlashForge Adventurer. The leveling sensor sits behind the print head shroud. Adjustment requires navigating 3 menu layers, and you're working by feel because the enclosure limits sightlines. But here's the honest friction for open frames. You're servicing them about 40% more often. Dust accumulates on linear rails. Belts need tensioning every 80 to 100 hours. I spent 15 minutes per month on average maintaining the Ender across a year of moderate use. That's 4 to 6 prints weekly. The FlashForge needed 8 minutes monthly, mostly nozzle cleaning and bed readhesion checks. Enclosed printers hide complexity, which helps beginners but delays mastery. The Bamboo Lab A1 Mini's Just Works experience produced perfect prints for my 10-year-old tester until it didn't. When a thermistor failed at hour 187, we waited 3 days for a technician video call. Meanwhile, the Ender 3 thermistor swap took 12 minutes with YouTube guidance and a $6 part from the kit I keep stocked. This is really the progression question. Do you want your kid printing reliably in week 1 with an enclosed printer or diagnosing belt tension by week 3 with an open frame? For learners targeting engineering careers, the open frame path builds skills that transfer to CNC machines, laser cutters, and industrial automation. If you're building a progressive learning path, consider starting with a beginner-friendly enclosed model, then graduating to an open frame as a capability unlock purchase 12 to 18 months later. Connectivity matters for supervised learning too. The FlashForge connects via USB-A, microSD, or cloud slicing. That requires account creation but no subscription. The Bamboo Lab demands Wi-Fi and cloud slicing for full features. Great for remote monitoring from your phone, but problematic if your workshop has spotty connectivity. Open frame printers typically use SD cards, which teaches file management but requires physical media swapping. Now let's talk about print quality and dimensional accuracy. I've measured over 500 prints across both designs with digital calipers and surface roughness comparators. The difference is smaller than marketing suggests, but real in specific scenarios. Enclosed printers deliver 0.05 to 0.08 millimeters better dimensional accuracy on prints exceeding 100 millimeters in any axis. This matters when you're printing multi-part assemblies, gears that need to mesh, snap-fit enclosures, articulated joints. I printed a 12-part robotic gripper on both platforms. The FlashForge version assembled with light finger pressure. The Ender 3 version needed 10 minutes of file and test fitting on 3 joints.
Layer adhesion is identical for PLA on both designs. I've torture-tested prints by clamping them in a vise and measuring break force. PLA parts fractured at 285 to 310 newtons across 6 samples, regardless of printer type. But PETG layer adhesion on open frames dropped 18% in my cold garage at 14 degrees ambient. The same prints on the enclosed FlashForge stayed within 5% of spec sheet strength values. Surface quality depends more on speed settings than enclosure. I ran 0.2 millimeter layer height test prints at 60 millimeters per second on both platforms. Visual difference? Negligible in simple geometries, but the enclosed printer's stable temps eliminated the banding artifacts I saw on the Ender when garage temps fluctuated during prints over 4 hours. If you're printing cosmetic parts for science fair projects, that matters. For functional prototypes, not really. Bridging and overhang performance actually favors open frames by 10 to 15% because of better cooling airflow that prevents sagging. The Ender 3's dual fan setup directed air exactly where needed. The FlashForge's single enclosed fan couldn't match that focused cooling. 45-degree overhangs showed slight drooping where the Ender stayed crisp.
But honestly, you should be designing with supports anyway if overhangs exceed 50 degrees. This is a minor factor unless you're chasing competition-level prints. Resolution specs are mostly marketing noise. Both designs hit 0.1 millimeter layer heights reliably. I've never needed finer for educational projects. The real difference maker is first layer consistency, where enclosed printers' stable bed temps win decisively. I logged 96% first layer success on the Bamboo Lab versus 87% on the Ender over 100 prints each, both using auto-leveling. That 9% gap translates to wasted filament, wasted time, and frustrated kids. So who should actually choose an enclosed frame printer? You're the right fit for an enclosed design if you're serious about material versatility and can't provide constant supervision. Pick enclosed if you're planning multi-material projects, ABS for impact-resistant robotics components, PETG for outdoor durable solar panel mounts, or nylon for living hinges. These materials require controlled environments that open frames just can't provide without DIY modifications. You need walk-away reliability. Maybe you're running prints during dinner prep or overnight. Enclosed printers let you monitor via phone app. Models from Bamboo Lab and FlashForge do this, without line of sight. The safety interlocks mean if your 9-year-old wanders into the workshop, they can't access hot zones mid-print. Your workshop environment is challenging. Basement with 40% humidity swings, garage that hits 10 degrees Celsius in winter. Enclosed printers compensate for bad environments. I've run the FlashForge Adventurer in unheated spaces where the Ender 3 flatly refused to print PETG successfully. You're preparing for industry-standard workflows. Professional additive manufacturing uses enclosed chambers. Think Stratasys F370, Ultimaker S-Series, Markforged systems. Learning on an enclosed printer teaches the same safety protocols, material handling, and print preparation that internships and college labs expect. If your teen is eyeing mechanical engineering or industrial design paths, this matters more than the $300 price premium. The downside? Limited learning from failures. Enclosed printers are appliances, reliable but opaque. Now, who should choose an open frame printer? Open frame designs are the better choice when you're co-learning with your kid and PLA meets your project needs. Pick open frame if you're focused on PLA projects for the first 12 to 18 months. PLA handles school projects, decorative prints, and most functional prototypes perfectly. You'll save $200 to $350 up front, which buys a lot of filament and accessories. Better build plates, hardened nozzles, direct drive extruder upgrades. You want hands-on mechanical learning. Open frames are like Lego sets for understanding motion systems. Your kid will learn belt tensioning, limit switch calibration, stepper motor theory, and PID tuning. These are concepts that transfer to CNC routers, laser cutters, and industrial automation. I've seen 14-year-olds who started on Ender 3s confidently maintain $8,000 laser systems 2 years later. You're available for active supervision during prints, especially for users under 13. Open frames require this anyway due to exposed hot zones and moving parts. If you're already planning co-learning sessions, and I recommend this for building progressive capabilities, the safety trade-off is manageable. Budget matters, and you're comfortable with tinkering. That $250 Ender 3 V3 SE will need 20 minutes of assembly, bed leveling verification, and test print tuning. But you'll learn the machine inside out, making future maintenance trivial. Compare that to the Unbox and Print FlashForge at $550. Convenient, but teaching fewer mechanical skills. The honest friction? You'll troubleshoot more. Failed prints, adhesion issues, periodic maintenance. Some families find this educational. Others find it frustrating. Let me address some frequently asked questions I get about this topic. First, can open frame printers safely print ABS filament if you add ventilation? Open frame printers can print ABS with proper ventilation, and I mean an outdoor exhaust fan rated for VOCs, not just a window, but they'll struggle with warping and layer adhesion in ambient temperatures below 20 degrees Celsius. I've successfully printed ABS on open frames in summer with a box fan exhausting fumes and a DIY cardboard enclosure maintaining chamber temps around 35 degrees. I achieved about a 70% success rate, compared to over 95% in a properly enclosed printer. The bigger concern is exposure. Even with ventilation, styrene VOCs can reach levels that cause headaches during prints over 4 hours. That's why enclosed printers with HEPA filtration are the recommended path for regular ABS use with kids present. Second question, how much harder is maintenance on open frame versus enclosed printers for beginners? Open frame printers require approximately 15 to 20 minutes of monthly maintenance. That's belt tensioning, rail cleaning, nozzle checks. Enclosed models need 6 to 10 minutes in my year-long comparison testing. But the open design makes diagnosis dramatically easier when problems occur. I've watched beginners correctly identify bed leveling issues in 3 minutes on an Ender 3 versus 15 minutes of menu navigation on enclosed printers, where you're troubleshooting by inference rather than direct observation. The trade-off is frequency versus learning value. You'll service open frames 40% more often, but each maintenance session teaches mechanical principles that transfer to other tools in a home fabrication lab. Third, do enclosed printers prepare kids better for professional additive manufacturing careers? Enclosed printers mirror industrial workflows and safety protocols used in professional settings. Stratasys, Ultimaker, EOS systems all use enclosed chambers. They teach material handling, chamber temperature management, and hazard mitigation that directly transfer to engineering internships and college labs. But open frame experience builds deeper mechanical troubleshooting skills that technicians and maintenance engineers need. The ideal progressive path is starting with an open frame for foundational understanding, then graduating to an enclosed model when projects demand advanced materials or when the learner is ready for industry-standard CAD-to-print workflows around age 13 or 14. Here's my bottom line. The debate between enclosed versus open frame printers for kids resolves to supervision capacity and material ambitions. I've placed dozens of families with both designs over the past 8 years.
Choose enclosed if you're printing ABS or PETG, need walkaway operation, or your workspace has temperature swings exceeding 10 degrees Celsius. The FlashForge Adventurer 5M Pro hits the sweet spot at around $550. Check the link for pricing. It's got genuine HEPA filtration, intuitive controls, and print quality that 95% of youth projects won't outgrow. It's the right first printer for families who want reliable results while learning 3D design fundamentals. Choose open frame if you're committed to co-learning, comfortable with hands-on maintenance, and focused on PLA for the first year. The Ender 3 V3 SE at around $250, check the link below, is 80% as capable for PLA work while teaching mechanical principles that enclosed designs hide. It's the better choice for teens targeting engineering paths who will eventually want to modify, upgrade, and truly understand their tools. Or do what I did in my workshop. Start with a $250 open frame for foundational learning, then add a $500 enclosed model 18 months later when projects demand better materials. 2 printers mean parallel projects, backup capacity when one's down for maintenance, and a complete capability set. That $750 combined investment builds skills from mechanics through material science. That's exactly what progressive learning looks like. That wraps up this episode of the STEM Lab podcast. Thanks for spending this time with me. New episodes come out every Monday, Wednesday, and Friday, so you'll always have something new to listen to. If you found this helpful, I'd be really grateful if you could leave a 5-star rating and write a quick review. It sounds small, but it actually makes a huge difference in helping other parents and educators discover the show. And if you haven't already, hit subscribe or follow so you get a notification the second a new episode drops. See you in the next one.